Hello everybody, how's it going? Leo here, and today we have quite the video. So, have you ever tried to make visual effects that actually adapt to the game objects on the scene? That is sometimes a challenge, especially if you're using Shuriken, which is the default Unity particle system. The new VFX graph actually is smart and can adapt to the actual gameplay going on. It has incredible scripting interfaces, and you can even make the VFX smart. However, on the previous particle system, you can't do that. A while ago, we were making a beam slash ray slash laser beam type of thing for the Unity Asset Store, and I had to develop an actual script that makes the beam's endpoint and start point and impact point, adapt to whatever game object you choose. I'm going to teach that information, I'm going to relay that information and pass it forward on this video. It is a little bit scripting heavy, but trust me, it is worth it, and the results speak for themselves. So let's jump into the engine. Alrighty folks, onto Unity we go. We can see here the final product of what you can expect to make. Now, of course, these little beams here, they are from a VFX pack that we sell on our Unity Asset Store. And I'm not going to teach necessarily how to make these exact beam effects here, but what we're interested in this tutorial in particular is the behavior. So you can see here that we have a casting point effect, an impact effect, and on the middle we have some particles, but we also have on the middle some line renderers. So allow me to demonstrate something that is the bread and butter of this effect. Here on my fire beam, I have this impact point game object, and as I move it around, you can see here that the effect adapts to the new length of my beam. So I can move the impact point anywhere I want, and it's going to look all right. And you can see here, if we let it loop for a while, you'll notice this has a certain particle density. Those fire little specks, they show up in a certain density. And even if I stretch it a lot, you can see that the fire density is kept. The number of particles is consistent to the size of those particles. So this is the magic here that we're going to do. And it does use a very simple script to help us out. And I'm going to be teaching you how to make this script in specific, since the script is really the bread and butter of this tutorial. I'm actually going to use, for the example purposes here, we have a bunch of different beams, but for this example in particular, I'm going to use this purple one because it has a lot of properties that, interests me as an example. You can see here this effect. I can isolate, for example, and remove those little spheres, and you can see that the beam here only uses 2 line renderers. And as I change the impact point, you can see here that the line renderer adapts. So this works for line renderers and particles. And our little particles here, if I replay them, you'll also notice die off once they hit the impact point. The impact point is really just a looping particle system with a bunch of particles, right? We can just disable it. We have an activation effect as well, which I can show you here. And the activation effect and the cast effect are also just looping particles. This is just a regular old particle system, nothing special about it. These 2 elements here are also not relevant to this tutorial. The part that's really tricky to achieve is this one, right? This is the difficult part to achieve. If I click here, they're going to update. This is going to be the main focus of the tutorial. But what we're going to do here is that I'm just going to right click on my project anywhere. I'm going to delete the script later, and we're going to make a new C# script. And we're going to call this particle beam. Well, you can call it whatever you want, but I'm going to call it particle beam. All right, so here we have our particle beam script. Here on this particle beam, we want to do a couple of things, but I think it's important for us to kind of understand the concept before we start jumping into the code. The main idea here is that first, let's ignore the line renderers, because the line renderers, they're really easy. They just have this positions here, and this positions variable is exposed to code. So all you gotta do is synchronize the start and end position to the starting position of your beam and the ending position of our beam. In this case, I'm using the end point as this impact point. So as I move it around, I update the main beam variables here on this positions array. it's very, very simple stuff. This is why I don't think it's worth it going too much over it. Of course, we're going to still code it, but it's very easy to understand. Now, the twirls here, the little particles, are a little bit more interesting because you see, the way we do this is that we use a custom shape through the shape module. And here on the shape module, we actually use as edge. And what the edge is really just a line. The way this works is that as we increase the radius of this edge, the edge gets bigger and bigger. But whenever we move this stuff, we also gotta fix the position so that it starts alongside the length that we want it to have. Essentially, if the radius is 7, we want the position here to be 7 as well. Something else is that as we move this along, you can tell here that the rotation changes. The idea really behind this is that we're using the edge and we're starting it at a pivot of 0, since if we increase the radius and the position on the Z by the same amount, we're essentially making it so that this edge starts at the pivot point and points outwards, right? Then all we gotta do is make this object rotate towards the impact point, and it's always gonna be a match. Our simulation space needs to be local for this to work best, but under some circumstances, if you want the particles to kind of lag behind a little bit, you can use world position. That's not a problem. And there's also other tricks that we can use, but I'm going to cover them a little bit later to make the particles disappear when they reach the end. There's a little trick there that I'm going to show you later. The very first thing we need, of course, is to actually have the variables so that we know what we're manipulating. So in this case, we're going to be manipulating line render and particle systems. We likely want to display that here on our coding. So what I'm going to do here is that I'm going to create a new list, and it's going to be private. So let's make a serialized field, which essentially displays it on the editor. Let's call it private. It's going to be a list, and it's going to be a line render list. So we're going to call these beams, and then you can just tab out here and it's going to work out. So now we have a variable to save all of our line renderers. Something else is that we also need particle systems. Let's once again serialize field. Let's make a private list, and this time around it's going to be particle systems, and we're going to call this, we can call it particle systems. Let's call it beams systems, just so we have a little bit of equivalence in the naming. This is great. So if you look in here, you realize that what we use to tell the beam where to go really is just this impact point. So we also need a variable to tell the code what our impact point even is. So let's go over here. Let's make, once again, serialize field. And we're going to do a beam target. Let's just do a private. We only care about the position and rotation, so this is going to be a transform. And we're going to call it beam target. Something else is that we want to sync the rotation of our impact VFX to the casting angle. And to do that, we're going to need also a reference or beam target hit visual effects. Let's do here game object. I think we don't even need a game object. I think we only need a transform, but I'm going to put a game object for now. We can change it later. So let's call it a beam target hit effects. Something else that we also want to set in the future is that this little line renderer here has a width. You can see here, if I make it 3, you can see it becomes really thick, right? If I go back to 1, it goes back to normal. We want to have control over that. So what we can do here is that we can do a private, and we can do a list of floats. Why is it a list? Because we have multiple line renderers. So if we have multiple line renderers, we also need multiple width values. And we're going to call this desired, desired width. This is a hard word to spell. Let's just make a new list there. Also, something else we want is that you can see here, I already showed this, but just reiterating that as I move the impact point, no matter how small or big I make it, the particles, they keep their density intact. So this means that we also want to save the density of those particles. So what we can do here is that we can make a private, and this is going to be a little bit weird, but we're going to do Unity Engine, we're going to do particle system, and from the particle system, we're going to get a min-max curve. And this is going to be our default density. We can just tab out there on the list creation. The important thing about this default density here, it needs to be a min-max curve, because when you go to your particle system, you can pick a minimum value and a max value, and it can also be a curve. And the way Unity stores these values for spawn rates for anything on the particle system that has a minimum and a maximum is through this weird little variable type min-max curve. Even if you're not using those values, even if you're just using, the same variable every time here on the emission, like in this case, we're using just a flat out variable, but still, you need to use that variable type. So now that we have all of that, I think we're actually ready to begin the code. So the very first thing that I think we should do is that we should, well, populate these variables. That's what we should be doing. Let's go out and just populate variables from editor. This is going to make our lives a lot easier. The first thing we're going to do is just get all of the line renderers, get all of the particle systems, do all of that. We can make a private void, get child line renderers. Oops. A little bit of spelling mistakes here, but there's a huge microphone in front of my keyboard, so I apologize. We have this. The very first thing we want to do is that our line renderers, they're saved on this line render list called beams. We want to write things into this variable, but we got to make sure that this variable is clean. And since this is an editor script, it could be the case like, well, this script has runtime capabilities, but it's also going to be ran on editor. So it is important for us that this variable is proper clean. We start off by saying beams.clear, just so we have a clean slate. Then what we do is that for each child item on our particle system, we want to check if they are a line renderer. And if they are a line renderer, we're going to add it to the list. So we're going to make a for loop. Very simple, right? We're going to do a little bit of that. And what we're going to do here is not actually this. We're going to say the transform of this script, right? Whichever game object it is attached. And we're going to do dot child count. And this is going to loop through each child from this object. And then inside of it, we want to check, aka if it has a line renderer. So what we're going to do here is that we're going to do transform get child I. And what we're going to do here is that we're going to say try and get the component. And the component you want to get is the line renderer. And if you can, you take it out as a variable. So this is how you say that. You say line renderer, and then we can do here underscore line renderer. Now, what's going to happen here in this if statement, what's going to try to do here is that it is going to check for the child number I and attempt to get this component as a variable. And if it can, it's going to run through this logic. The logic is thankfully very simple. We're just going to get our beams variable and we're going to add the underscore line renderer since it's the reference for the component that we just got. So now, whenever we run through this code here, we're going to get a list of line renderers, which is pretty neat. What we can do here as well is that you go here on window. Well, my editor is going to lag a little bit because we wrote a little bit of code. Well, let me just wait for it to compile.
A few moments later.
So what I recommend you do is that you go to Unity and you find this little plugin. It is free and it is incredible, called Naughty Attribute. I really like this little plugin here, and it has this button method. And what it does is that it exposes a function as a button on the Unity editor. And this is incredibly useful because here are my void ray. Let me actually remove the old script here. It's going to break everything, but it's fine. And if I add my particle beam, we do have a bunch of variables here, but we can't really test that code very easily without playing the game and putting it on start or something. But with Naughty Attributes, what you can do is that you can simply write button here. I already have this thing, but if you don't, I recommend you use Naughty Attributes. Mine is a little bit different. Mine is button method. Naughty Attributes is just going to be button, but that's fine. If I go over here, we can see here we have the get child line renderers. And if I press it, we go to our beams, we have the reference to both of our beams. Now we can test and we can assure that this is actually properly working. So now any child of this particle system here that is a beam will be added as a reference here to our little script, which is great. the next thing we're going to do here is that we also need to get references for our beam emitters or particle system. So once again, same deal. Let's make a private void get child beam emitters. We're interested on the actual particle systems, right? This time around. Once again, same logic applies. We want to make sure that this variable is actually completely clean. So we do the name of our little list.clear. So beam systems.clear. And then for int we already have that. Child count. All right, that's actually pretty good. The code is helping me out here. The autocomplete really is doing the heavy lifting. So for each one of our childs on this transform, we're going to check if it has a particle system. So same thing. We're going to do transform get child, and we're going to do I here, and we're going to do try get component out particle system, and we're going to call it _PS. So we're doing the same thing as before. We're checking if this child has the particle system component, and if it does, we're getting it as a variable to use inside of these brackets here. So now, in here, we need to check if the particle system shape is an edge, since those are the only ones that are going to be used as a beam emitter. What do I mean? Let me show you. So you can see here that this is the parent. And this is where our particle beam script is attached. And we have the twirls, which should be a beam, but we also have, for example, the activation, the cast, the impact. All of these particles should not be added into the logic. Only the particles that use the edge shape here on the shape module on the particle system, because these are the ones that are going to be laserfied, if you will. We got to check for that. So Unity doesn't make it very easy to work with this type of stuff. What we got to do first is get a reference for the shape. We can't just compare it directly. First, we need to turn that reference into a variable. So what we can do here is we can do var, and let's call it sh for shape, and it's going to be equal to _ps, which is the particle system that we got, dot shape. Simple as that. We're just reading the shape of that particle. Then we're going to do if sh dot shape type, and if the shape type is equal to, and now here comes the tricky part, we actually do particle system shape type. And yes, this is a type on Unity. And on the dot here, you're going to find single-sided edge. Oh, it's actually one of the first ones. Cool. So this is the code name for the edge shape. If this condition is true, so if the child has a particle system attached and it has the correct shape, then and only then we want to do beam systems.add _ps. So we're adding it into that variable, and we can verify if this code is working right now. Now, of course, you don't need naughty attributes for this. You could do something like, you know, force this to run on awake or whatever. But I think it's just easier for us to make a button method here and click the button. All right, so here we have our void ray. And if we click the get child beam emitters, we should only get the twirls. This game object right here. I think that's the only one we should get. Let's try it out here. Get child beam emitters. We expand here. Indeed, we only got one, which is the correct one. So this means that our algorithm is working. The next step here is kind of an interesting one. Let me get here my void ray here for a second, and let me show you some other examples of beams here. So let's get like the holy ray, for example. And the consistency of the density of these particles is kept the same no matter how much I stretch my particle. You can see here that the density is the same. You're going to notice, for example, that these little let me disable the beam here. So these little twirls, they're spawning about 45 particles at any given time. Let's call it that much. The glints have 80-ish, 75, 80, something like that. Smoke has 80 as well. Even though their density is kept whenever I manipulate the impact point, different particles have different densities. And to do that, we gotta essentially figure out a base size in which all of our rays are built. And whenever we're making a ray particle, we first make it at that given size. We choose whatever density we feel like works best, and then we cache it on the code. What we can do here is that I can go over here and essentially we need to go through each of these particles and save the particle density for later. So we can also make this a button method. And let's call this private void cache particle density. In this function here, what we're going to do is that we're going to set the default density. So this little guy here. So once again, if we want to set it, we want to make sure it's actually cleared of impurities first. And then what we want to do is very simple. We just want to go through every particle and save their spawn rates. Very, very simple. We already know the particles that we have from the beam systems, right? What we can do here is that we can do a for loop. And in this for loop, we can do int I, blah, 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 like that. And while this count is smaller than beam systems.count, we want to keep looping because we already have cached away. Oh, sorry. Hold on. I want to compare I to it. Great. Because we already have saved which of our particle systems could be part of the beam. So we only need to save those. So what we do here is that we go default density, add, and what we do is we do beam systems and we get the member I, and we go for their emission node rate over time, which is the one we care about, dot constant. This does means that the rate needs to be constant. You cannot have randomness. You could easily modify this code to work with that, but I feel like on this beam system in particular, you just want to use constant every time. So this is what we're going for here. This is going to suit 99% of use cases. Now we have, I think, every single dependency to start getting our particles to move correctly, which is great. Something else you could do, which I do think would be smart, is for you to remove all of these little button methods here. And what we can do here is that we can make a private void, assign default beam data or something, you know, just create a function here. And inside of this function, what we can do is that we can get our child line renderers. Not only that, but we can get our child beam emitters. And finally, we can cache the particle density. So we can have all of that in a single button, which I think it's a very clean solution and, you know, works really well. So now if I go back here and I wait for my stuff to compile, I can just press that one button and everything will be set up. So if I go here to my void array, we have this assign default beam data. I click it and, well, we don't see any changes because we already had this data before, but it has worked. I'm very, very happy with it. Well, I guess we can check out the default density here, and it is indeed set up with the density that we have on the little twirls here. Now we have all of the relevant variables from the hierarchy onto our script. So what we can do here, this is just for organizational purposes. You don't need to do this, but I'm going to do this just so the tutorial is a little bit cleaner. I'm going to do a region. We're going to call this getting editor data. And at the end here, what I'm going to do is that I'm going to do end region. And now we can just click this little thing and boom, forget that this code even exists. We're not going to be touching it anymore. All right, so what we're going to do now is that we're essentially going to make it so our edge systems update. Actually, no, let's do the line renderers first because they're just easier to do. So let's just create a new particle system here, just so we have the full workflow. So this is going to be our tutorial beam, and let's add our particle beam script to it. Inside of it, well, I also want to add particle system component here. This is just so the child particle systems also play. Let's delete the void and the holy beam there, and let's decrease the emission. Let's disable everything here. This is just so the child particle systems will play. So what we can do here is let's create a new effects particle system, and this is going to be our tutorial edge. No, let's do line renderers first. Tutorial line renderer. It's not going to be a particle system, actually. It's going to be a line renderer. How great! Here we have it. Hooray! We have a simple line renderer that's just pink. And doesn't look that great, but hey, what can you do, right? I guess we can just apply any material here. These materials are just from like Piloto Studio assets. So let's just slap a random material here just so we have something pretty to look at. So we want to update our line renderers every frame to the correct position, to have the correct start point and the correct end point. We have here this function, and you can see that we're calling this function on update. So pretty much every frame, and it should tell subscribe to Piloto Studio. But if I go over here, you can see that nothing. There's nothing. There's no comments, anything. For this to work on the editor, when you're working with particles, you're usually working on the editor. So it's useful for you to have this view on the editor as well. So what you can do here is that high above everything, you can say execute always. What this tells Unity is that this script could happen even when you are on the editor. So now if we go back here, and we can see here, we're getting a bunch of subscribe to Piloto Studio, subscribe to Piloto Studio, subscribe to Piloto Studio, which is great. Yes, this is exactly what we need. Now, what we can do is that if you remember on our little editor data there, we had a button, a sneaky button, and that button could get us our line renderers. So what we can do is that inside of this function, we can do for each line renderer. So for each line renderer, and we're going to call these line renderers _line. So we're giving them a name. Inside of our list of line renderers beams, so for each one of those, what we want to do is that we want to take this particular line that we named _line, and the first thing we want to do is tell them to use world space. This needs to be true. Technically speaking, if you had set it up to always, if you set it up correctly to be true, you wouldn't need to do this. But I think it's good to double check and always set it to true. Otherwise, it's going to look very odd. And then on our line here, we want to set its position. This position is an array. So we want to get the member of the array number 1, which is essentially the starting of it. We want to set it to be the pivot point. So _line.transform.position. So we want this line to start on its pivot point. Then what we want to do is that we want to do _line.setPosition, and we want to go 0, and we want to do beam target, which is a variable, .position. Something to note here. You might have noticed that I start at 1 and not 0. The reality is that you can flip these values, and it's not going to make much of a difference. The reason why I personally like using 1 and 0 in this order specifically, it's because the line renderers are flipped in relation to trail renderers and to Unity particle systems trails. So the materials that work in one are going to be flipped on the other. So what I do is that on the code, I flip them again so that they're equivalent between each other. Just test it out. If your material looks flipped, you can just flip these to be 0 and 1 respectively. So now, if we go over here, it's probably not going to work, now that I think about it, because we haven't pressed the button here on our tutorial beam. So let's do assign beam data, and immediately we have this little effect going. It's throwing out an error at us that we don't have a specific variable called beam target. So let's create one. Let's just create a new empty game object, and it's going to be called beam target. And what we're going to do here is that on our beam target, we're going to populate this variable. So now if we move this around, you can see here what's happening. Our beam is following along, which is exactly what we want. So this is actually pretty good. And this is all you need for the line renderer logic. It's that simple. You don't need anything else. We still haven't addressed the particles though. Let's do that. So if I go back here, play line renderers, let's collapse this little thing. Now let's create a new private void, private void partial. What the hell is partial? Called play edge systems. And in here, God, my keyboarding today is not good, huh? In here, we want to do similar things that we did with our particle line renderers, right? So the first thing we want to do is that we want to do a for each loop. This for each loop is actually going to be between particle systems, and we're going to call these particle systems _PS. And it's not going to be inside the beam system. Well, it is actually. The autocomplete got that one correct. Beyond. The first thing we want to do, and something that I kind of alluded before, is that the edge is just going to point towards the direction of the finish, and it's going to have the same length necessary to achieve the direction of the finish. This means, let me get here some more particles again, just so we can kind of understand here. If I get these leaves here, for example, We just deactivate a bunch of stuff. If I go here for those little, well, yeah, these ones, for example, the way that they get synchronized is that we're setting the length of the shape should be correct so that it matches from start to finish. And then we're just changing the angle so that it looks towards the impact point. So let's go here on our tutorial beam and let's create an effect particle system. And let's just use here the default particle that Unity uses. You know what I'm saying? Let me see here if these are going to work. All right, great. We have some default particles just doing particle things. What I'm going to do is that I'm going to decrease their lifetime should be 1 and their speed should be 0. And here on the shape, instead of being on a cone, we want to change it to be an edge. And there we have it. We have just an edge, right? Very, very simple stuff. And we have those particles spawning in. All right, that's great. Let's click the button once again here on the assign default beam data, which also assigns the default density, which is really interesting. And what I'm going to do here on our code is that we want to go quaternion. And quaternion is the way Unity handles rotation. We're going to create a new variable called look rotation. And this is going to be essentially quaternion dot look rotation between our beam target dot position minus the particle system in question dot transform, oops, not trails, transform dot position. And something important here is that this look rotation needs to be normalized. We're going to normalize it. Now that we have this variable, we're going to go underscore ps dot game object dot transform dot rotation, which is going to be equal to look rotation. Great. All we're doing here is that we're forcing this particle to look towards our target. So let's also call it on the update function. Let me even comment here, fixing rotation. Now, next step is that we need to make the shape length equal to the distance between a particle's start and end point, between our beam's start and end point. Once again, we cannot manipulate shapes directly. We need to make a variable. So let's create, we did this once before, let's create a var sh. This is going to be equal to underscore ps dot shape. Now, what we're going to do here is sh dot rotation, and we're going to make this essentially straight on the 90 on the y-axis. So we're going to do new vector 3, 0, 90, 0. We do this so that we align the beam with the forward direction. We need those things to be equal because we're setting the rotation, the particle to look on the forward direction towards the impact point. So our shape also needs to be consistent with that. We're zeroing things out. Then what we do is that we're going to make a float, beam length, and the distance between something is just the start point minus the end point. So that's exactly what we're going to do. We're going to do vector 3 dot distance. There's actually a function for that. It's going to be beam target dot position, and it's going to be underscore ps dot transform dot position. There's a trick here. We need to divide it by 2 since it increases on negative and positive axes. So essentially, you're going to notice here, well, maybe I should do this. What I'm going to do is I'm going to divide this by 2, and then we're going to remove this division so we see what happens. It's very visual to explain. And what we're going to do is that we're going to go to our sh.radius. Once again, we need the variable. We're going to assign it to be equal to the beam length. But we also want to go to our shape here, and on the position, we want to essentially add the length to the starting position, beam length. Great. And the reason why we want to do these things, and also it's partially the reason why we divide it by 2, is that we want to make the pivot of the particle system also the starting point of our shape. With this little logic here, we should be golden. Now if I play here, it's going to take a while to compile. But now you can see that, all right, the particles are very much consistent. And so you can see here what I mean. If I select my particle system, you can see how the pivot point of the particle system is also the starting point of the beam. Because if we don't change the position, so let me just disable here this particle system. If we go here on the shape, you can see that the length is 2.6 and the position is 2.6. If I make the position 0, you can see what happens here. It just goes from the middle outwards. So we need to add the length to the position so that in this way the pivot point is zeroed out. All right, great. This stuff is working. Now, this is already the more basic setup, and you can tell here that it more or less works. There's some problems here, though, that are really details. And if you don't care about those things, you wouldn't necessarily need to go over this. But I think it's important. Those things are the density of the particles. That's the first big one that we need to address. You can see here that if I go for my beam target and I extend it outwards a lot, trail works fine, but the particles, they're really spread out. They're really far apart from each other. And we want those particles to be more dense. And ideally, we want this density to be kept, right, the same across multiple systems. What we can do here is that let's establish that this is the desired density that we want to have. On the code, we have this play edge systems and play line renderers, right? We have those little things here. What we can do here is that we also need to update the particle density. So let's create a private void, update particle density. So now inside of here, we're going to need a couple of things. So the very first thing we need is to know the distance between our start point and end point so that we can, make math based on that. So let's do float distance. And you all know how distance is done. There's even this handy little thing here, distance. And we can just do this dot transform dot position, and then we can do beam target dot position. Now we have this distance. There's a little trick here, and this is something that you don't necessarily need, but I personally like using. I use all of the particle systems that I make with the beam in mind. They have a default value, right? The holy grail, where I author them to look good at one particular distance. And then I just want to scale it out to every other distance. In my case, the distance that I use is 5. So what I do, essentially, before authoring these particles is that I go into the beam target and I make sure that the position is 0, 0, 5. What this means is that whichever density I choose here is going to have this starting point of 5, and it's going to have this base value of 5. I want to account for that on my distance calculations. So what I can do is that I can do distance and say, hey, distance, you are equal yourself minus 5. Since this is kind of our default baseline. 5 is the baseline of our particle systems. What we want to do here is that if distance is bigger than 0, which also means exceeding 5, right, in some way, shape, or form, we want to apply a distance multiplier to the particle system's emission. What we want to do here is that we're going to create a new float called distance multiplier. And this distance multiplier is going to be 1. We always want it to be 1, so we have a base value of 1. Of course, everything you multiply by 1 is itself. So this is why we have this base value of 1, so that if the distance is very low, it can't multiply below 1. And then we want to say that it's 1 plus distance divided, once again, by 5, since that is our baseline. And then we're going to make a for loop here once again with our beam systems. This is actually kind of impressed that they guessed correctly. The IntelliSense is getting better and better. We're going to save our emission on a variable. And once again, this is a module of the particle system, so you cannot do this straight up. You need to save it on a variable. We're going to do beam systems I dot emission. We're going to save it out on a variable, and then we're going to take this variable emission, and we're going to take the rate over time, and we're going to say that it is equal to, remember the thing we saved before, the default density? Well, we want to get the default density for that specific particle, which is constant, and we want to multiply it by our distance multiplier. Oops, distance multiplier, the second one, not the first one. The thing is, 5 is our baseline. So what happens if distance is actually below 5? What do we do then? What I have essentially chosen to do is to reset it to baseline. So if it's below 5, it's going to be the value for 5. So that's the minimum. So we can do an else here, and we can do a for loop, and we can do I systems. Well, it's lesser than beam systems.count. And then we can do this. All right, so we have a for loop, once again looping through every single beam system. We're going to once again create our var emission here. Actually, you just copy this code here. And on this rate over time, instead of doing these multiplication shenanigans, we just want to do this. So we want to set it back to baseline. So now we have the update particle density. Great. So we want to play our line renderers, play our edge systems, and we also want to update our particle densities. Is there anything else I am forgetting? Yes, there is actually. there actually is a couple of tricks that I want to show you. This tutorial is running really long. I had a couple of other little improvements, but honestly, they're very, very small. They shouldn't matter that much. They're almost nitpicks from my end, but let's just wait here. We can see now that the particles, even if I spread them really far apart, their density is kept pristine, which is exactly what we want. And if we go to our beam target and we make it small again, so let's go back to like 5, you'll realize that the rate over time is restored to what it was. So one last tip before I leave is on cases like this. I use this extensively throughout my project. So you can see here that we have these little particle systems, right? And they're moving. They're moving towards the endpoint. And if I do this on our tutorial beam, you're going to notice, right? If I go here, velocity over lifetime, let's increase it a little bit. Yeah, that was too much. But you can see that they're bleeding over the endpoint, and we don't want that. The way you do this is that you're going to enable collision here in your particle system. You're going to set it to planes. You're going to zero out the bounce and everything, and on lifetime loss, you put it at 1. So here on the planes, you can click on the little plus sign to create a plane for you. And this plane, you just attach it to the endpoint. So what you can do is that you can attach it to like the impact VFX that you have. And you can see here that now the particles, they are killed off when they reach this endpoint. And this is how I get these little effects here. In my case, on these little assets here that we sell, I'm actually putting it on the impact VFX. I have this kill volume, and the kill volume is kind of what kills the little twirls. So I can show you here on collision. You can see what that looks like. You know, it's a pretty neat effect, and it's a way of making this even more seamless. And of course, if you don't want to follow along, you can just get all of this stuff for like $15 or something on the Unity Asset Store. Please don't forget to leave a like if you like the video, and thank you so much. Alrighty folks, thank you so much for watching. Don't forget to leave a like and subscribe, and of course, join our Discord on the description below. We are always posting stuff on our Discord. If you have any questions, you can also ping me or William directly there. Leave your suggestions for tutorials, and thank you for your time.